gas stoichiometry. So that just means that we're going to do a chemical reaction and create a gas, or gases are involved in a chemical reaction. So the last unit was, we did some gas stoichiometry, but we assumed the gases were at STP, standard temperature and pressure, and now we're actually going to measure the temperature and pressure and solve for that. And so we can't use the conversion 22.4 because that's related to if you're at standard temperature and standard pressure. Today, ironically, so usually April, we're nowhere near standard temperature and pressure because it's, usually like 70, 80 degrees, which is like 20 to 25 degrees Celsius. But, we're having an odd April day. And so it's actually really only supposed to be about 3 Celsius today. So that's pretty close to standard temperature. And the barometric pressure today, it's rising, but at like midnight last night, it was really close to standard pressure. So we're not that far off from STP today, just so you guys are aware. But we're still going to see how much that changes. Gas measurements. I know what else I was going to say. Last unit, primarily what we did, when you go from like grams of one thing to grams of another, when you're massing stuff on a balance, it's called gravimetric stoichiometry. And then we also did some solution stoichiometry. We were looking at the concentration of solutions. They're all just quantifying amounts in a chemical reaction, but what type of chemical reaction is kind of the label. So unless you are at STP, you're going to have to convert between volume of a gas and moles using the ideal gas law, because if we measure the temperature and pressure, this is a constant. If we know how much gas we want to make, then we can see how much volume it's going to fill, or if we know the container that we have and we're going to put a gas in there, figure out how much. Basically allows you the ideal gas law to get between volume and moles and volume if you're at a certain temperature and pressure. So the types of problems that you're going to do, though, you have to, if you're not in moles, you have to get to moles. And then if you're doing a chemical reaction, you might have to get from moles of whatever you're starting in to moles of the gas or vice versa. So these types of problems have a mixture of dimensional analysis and then manipulating the ideal gas law equation. So just framing the general idea here. Basically putting two skills together for the, what we'll be doing today. What I want you guys to do, find that mole map. It's that top 10 orange handout. And I'm going to have you guys add to it. So we have done like volume of a liquid to moles, use molarity. Number of particles to moles, use Avogadro's number. Grams to moles, use molar mass. Volume of a gas at STP is 22.4. But if you are not at STP and you want to go from volume of a gas to moles, you're going to use the ideal gas law. So if you're going from volume of a gas to moles of this, you're trying to solve for moles. So sometimes students like to add, so it's going to be moles, which is going to be the pressure volume of that gas over the ideal gas law constant and temperature. So if you're starting in volume of a gas, it's not at STP. And then let's say the chemical reaction makes a different gas and you're not at STP. So here you're trying to go from moles to volume. So here you're trying to find volume of that gas. You would be rearranging the equation that way. So just trying to show you where this fits in the framework of what we have been doing. So a lot of you are visual learners, and at least it just puts it on the map. You're welcome. And then we're going to apply this with an activity. So the making an airbag lab is what we're going to do. The bonus related to this is around car airbags. Okay, as new drivers, you should care how your car works. Let's be honest, a little bit. Not just, for like, oh, if I have a flat tire, I should know how to fix a flat tire. But, if I do get in an accident, what is going to save my life besides my seatbelt? How does that airbag work? It uses gas stoichiometry and some kinetics. Kinetics will be a different topic for a different day. But, so you have the handout, and what you're going to do is about. There is I don't think I have an intro video lecture on Dalton's law, but I might make it. We'll see where we get. Okay, so you can light hydrogen gas and oxygen gas in the right proportions and make liquid water and collect it. And if you use 20 liters of oxygen gas at a pressure of 2 atmospheres and a temperature of negative 35 degrees Celsius, how many grams of water can you make? It assumes, this problem assumes, it doesn't say this, but you have extra hydrogen, like the oxygen is the limiting reactant. Here, versus like the lab that you guys just did, you didn't have a limiting reactant. You calculated amounts of both to make a perfect ratio here. So, right, if you look at like, I want to know how many grams of water, and then look at the other numbers in this problem, you have volume of O2, you have pressure, that's just the pressure at which the reaction is occurring, and you have temperature. 2 atmospheres is not standard pressure, negative 35 degrees Celsius is not standard temperature, so you are not at STP, and so you will need to get there, or sorry, use the ideal gas law in order to get to grams of water. We have to get to moles of O2, and to then get to moles of water, to then get to grams. We have volume of oxygen gas. So if you look on, let's see, this, we're starting at volume of a gas, not at STP. We're trying to end up in grams of something different, just to frame it. So with that in mind, we need moles of O2 and of oxygen. And I recommend that you label what you have moles of, because you can only go between, so if you're using the ideal gas law, you can only go between moles of like oxygen and volume of oxygen. You can't go between volume of one gas to moles of something else. Does that make sense? Like it's just like you can't go from moles of one thing to grams of something else. You have to know how many particles of that thing that you have. So this is going to be our pressure, volume of oxygen over the ideal gas law constant times temperature. We have pressure in atmospheres. So I'm going to use the ideal gas law constant that has that. So moles of O2, we've got 2.00 atmospheres times 20.0 liters over 0.08206 atmosphere liters moles per Kelvin times this negative 35 plus 273. You're going to get 238 Kelvin. Always and forever for gas law problems, temperature has to be in Kelvin because that's proportional to the kinetic energy. The only unit that will not cancel is moles. I didn't say this yesterday, but if a unit is on the denominator of the denominator, like 1 over 1/4, a complex fraction, it's really equal to 4. So units on the bottom of the bottom. I don't need you to show the math, but I mean, dividing by this is the same thing as multiplying by the reciprocal. So this is really in the numerator, which should make sense since it's the only unit that we're not solving for. So we get, for the moles of O2 here, I have 2.04810 moles of O2. Yes, hold on. Okay, yes. I'm not rounding here, okay, because it's not the final answer. I don't want to like over round. If it just wanted moles of O2, okay, then I would round with sig figs, which I'd have 3. But we really want to know how many grams of water that we can take. So once we get this, it's just kind of, or then I would just take this in my calculator, and for every 1 mole of oxygen gas that reacts, you form 2 moles worth of water. And then in 1 mole of water, there's 18.02 grams. So we're making a little over 4 moles worth of water. Final answer rounded at the very end, 73.8 grams of water. This would be an amount that you get measured in the graduated cylinders that you just used, the 100 milliliter ones, not the 2. But notice that it's like a kind of a combo of using the ideal gas law and then the stoichiometry there. Questions on that one? It's a battle out there with them geese. Okay. One more, just because I think it's a cool application. You guys are new drivers, and I think it's good for you to understand, A, the combustion reaction that's happening in the car tank that you're driving. So I'm not spending our time balancing it because combustion reactions can have high coefficients, but for every 2 moles of octane that you burn, you need 25 moles worth of oxygen. You're going to form 16 moles worth of carbon dioxide and 18 moles worth of water. So if you burned 1 gallon of gas, which is approximately 4,000 grams, we're going to figure out how many liters of CO2 would be produced, and we're going to change it to the conditions today. So right now, let's see what it says for weather. Oh, it's a balmy 5.0 degrees Celsius. And the pressure is pretty spot on. It was 30.08 inches of mercury. So today, if you were to go drive around and just burn 1 gallon of gas, how much CO2 are you putting in the atmosphere? I think I'd want to know this, right? Like, you're a new driver. You go driving around town. I don't know. Maybe you'll be shocked, maybe you won't. Let's figure it out. We're starting with 4,000 exactly grams of octane. And we want to know how many liters were not at STP of CO2 we're going to put out. So a common thing with this, here you have to do the stoichiometry on the front end. So you can't, this is a liquid, the octane in your tank, and it's not at STP. So we need to first just get 2 moles of CO2 and then use the ideal gas law to get between moles of the gas to volume of the gas. So you'll do the stoichiometry at the end. So if you kind of frame it and you're like, okay, I want volume of CO2, that's going to be moles of CO2 times the ideal gas law constant times the temperature over the pressure. That's the rearrangement of PV equals nRT, but it's specific to the CO2. And then you're like, well, I've got grams of the octane. I have to get to moles of CO2 to then get the volume. So to start, sometimes you do the stoichiometry on the front end, sometimes you do it on the back end. It depends what you're solving for. So if we have 4,000 grams of octane, need the molar mass of it 8 carbons and 18 hydrogens. And then for every 2 moles worth of octane, we'll produce 16 moles of CO2. And you can put, yes, it is an 8-to-1 ratio. That's fine. But I'm just putting the coefficients from the balanced chemical equation. I get 114.26 for the molar mass there. So we're burning way more than a mole worth. It's like 35 moles worth. So 35 times Avogadro's number of octane molecules with 1 gallon of gas. Moles of CO2, 280.063 moles of CO2. So 280 times Avogadro's number. I don't know. Seems like a decent amount. Then for this, okay, we want the volume of CO2. So we have the moles, the 280.063 moles of CO2 times R. If you guys want to do atmospheres or kilopascals. We have pressure in inches of mercury, so we have to get to one or the other. So which R value? All right, well, I'm just going to use 8.314. We're going to have to convert kilopascal liters, moles per Kelvin. Our temperature, add the 273. We're at 278.0 Kelvin. Let me shift that over a little bit. All over, let's see, 30.08 divided by 29.92 times 101.3. Do our little conversion there. Pressure is 101.8 kilopascals. So 280.063. Let's see, what's our limiting sig fig? $4. So 6,359 liters of CO2. That's just 1 gallon of gas on one day in one car. We're not even talking about efficiency. This assumes all of it burned. You converted all of it to energy and maximized it and used it to fuel your car, all that stuff. And there's, close to 8 billion people on the planet. This is just from cars, not industry, not keeping the lights on. You think it adds up? All that CO2? Nah. Earth Day's coming up. You want to know who loves CO2? Trees. They love it. So plant a tree, okay? They're our symbiotic friends. And what we breathe out as trash, they take in as fuel and vice versa, okay? So if you guys like Planet Earth and that series and everything, they do a really cool, like where you literally like see the planet breathing, where you see like the winter time, like the leaves fall off and it change and then it all comes back and it gets green and it's like fluctuation and everything. Right now, as everything's blooming, more plants and whatnot are taking in more of the CO2. So we like in the northern atmosphere right now, we hit our low for the amount of like CO2 in the atmosphere. And then we build it back up as the year goes on until we reach springtime again. It's a cool little pattern. But I like this example for you guys. Okay, the lab activity we're doing tomorrow is an application of gas stoichiometry, but also this idea of partial pressures, and it's called Dalton's law. He was kind of the first person to look at it, and he was really interested in meteorology and that air is a mixture and everything. And most of the time, the gases that we work with are not pure. The reaction you just did was probably pretty pure because it was the only gas being made, because it wasn't really, there may have been a little bit of water, but because it actually, yeah, you made CO2, but it actually wasn't pure CO2 gas, because that gas was being bubbled out of an aqueous solution. And so oftentimes, how do we deal with gases that aren't pure? And how do gases behave? So we need to understand this idea of partial pressure, and then how do we work with numerically if we have a gas that is a mixture. So tomorrow, we're going to collect a gas, and it's going to be over water, and that gas is not going to be pure. So remember the other day I said there's dry gases and then there's wet gases? And is water wet? Well, that's a whole other thing we're not going to get into, but we will call the gas wet because it'll be mixed with water, because water will naturally vaporize. There's water vapor in the air right now. They call it humidity, and there's nothing we can do to stop it. But we can deal with that and back calculate so we can see how much gas is in there mixed in with the water. So basically to do this, to work with mixtures, which most gases when made are, we basically just treat each gas as if it were alone, which is fine because, well, gases really don't experience intermolecular forces. They don't really interact with each other, right? Kinetic molecular theory, which is one of our main theories of this unit, states that gases behave independently, they move randomly, they don't stick to each other. If they do stick to each other, they are not behaving ideally, they're behaving non-ideally, and when we do calculations, we're going to assume they're behaving ideally. Okay, so we're going to treat them as if they're much the same. So then as a result, if we can measure the total pressure of the mixture, we can actually say it's just the same as the sum of the partial pressures of each gas. In words, that's this equation. So total pressure is the sum of the parts, or the partial pressure of each gas. And depending on how many gases you have in a mixture is going to determine how many you add. If you have two, you just add one, one gas plus the other. You have 3, 4, etc. So for example, the air that we're breathing in is not pure. It's atmospheric pressure. So when we get this number 1 atmosphere, okay, which is Earth's standard pressure at sea level, what that really is the total pressure would be the sum of, well, the makeup of our atmosphere, which is made up of mostly nitrogen and oxygen gas and carbon dioxide and hydrogen and methane and helium and argon. Those are the main gases in our atmosphere. And each of those contribute partially to the sum of the atmospheric pressure, because each of those gases are in our atmosphere. So the 1, that's just like, we just standardize pressure, but that would be where that comes from. Because you're not like, oh, there's a nitrogen gas molecule hitting me. Oh, there's a CO2. Oh, there's a water molecule. Oh, there's oxygen. You're not like feeling the different pressures from all of them, but all of them collectively make up what we experience as Earth's pressure. Okay? Did I put? I didn't define partial pressure. Okay, so and then I'm just going to show you a picture because I think that helps with students. So partial pressure is defined as the pressure that each of the components in a mixture would exert if the other gases of the mixture were removed. So if you could isolate them. So basically, this is how they figured out the air composition, is they would find ways to separate the gases, measure them, and then measure their pressures. So a picture here is good for this. So in the first canister, you have 4 green molecules that are exerting 100 on this pressure reading. Obviously wouldn't be 4 molecules, but okay, but let's just say it's like 4 moles worth, is exerting a pressure of 100 kilopascals for this gas at a certain temperature. And this gas here, there's 10 red molecules, and they're also, you see from 4 to 10, it's exerting a pressure of 2.5 times as much. Okay, so amount of molecules is proportional. That's a true statement. This one is a diatomic gas, probably oxygen. This might be helium. This might be argon. I don't know. It's not a diatomic, but this one has 8, and it's 2 times the amount of pressure. If all 3 of these gases were put in the same container, what would we anticipate the pressure being? Yeah, we're going to add them all up. But I think a picture is worth more than the words that I've said. So, right, like basically be taking this and breaking it down into the components, but pressures are summative because the gases, they don't interact with one another, so they act independently, so we can treat each of their pressures independently. I'm going to end it there, but that is at least an introduction into that. There is on Schoology, let me stop this.